Good morning, everyone, and welcome back to the morning session of PLSS. I'm very excited to introduce our first speaker of the day. So this is Adám Brudzewsky. Adám is a lifelong APL programmer and creator of APL Cart, the APL Orchard, and many other APL-related things. He's the lead designer of the Dialog APL language. He and I first connected, in fact, over a shared joke about adding APL to JavaScript, an extension to the specification called staple, though I'm not 100% sure either one of us was joking. Please join me in a very warm welcome for Adám.
Good. I'm going to speak about a recent addition to the APL language as implemented by Dialog. But I'll start by going through some of the background for it. I'm sure many of you are not very familiar with APL, so we'll look at that, and then I'll take it from there. This is especially exciting for me because when we get to the implementation, we're just about to release our version 20, which has all of this finally in the product itself. I think we had like beta 4 or something. We should be there. I'm going to go through the history first, and this is going to be a shared history, just very brief, of both myself, because I'm a background about me, and about APL, because they're sort of intertwined. I'll start not at the right beginning, but I'll start in '62 when Ken Iverson published his book. And this is not intended, I think, to be a pretentious title. I don't think the phrase programming language was really in use at the time. And what he meant by this was a formal language to specify how systems could work, especially computer systems. And it was very much a mathematical notation. It was basically an extension of mathematics, linear algebra. Certain things were changed from mathematics, but very little. But there's a procedure of doing certain things, whereas mathematics tends to only describe how things are, but not sequences of actions. And this notation was used to design the IBM System 360. And that might sound old now, but this is really the precursor to all modern computing. You don't even realize how much we have to thank the System 360 for. Things we take for absolutely granted, like an 8-bit byte that comes from there. No way of separating memory and storage and all those things that nobody even thinks about today. It all comes from this system. And IBM, they basically bet everything on this. It was tremendously expensive. And if that had failed, IBM would have probably failed. But it succeeded. And here we are today in terms of this. And it had to be a really good, consistent, thought-through design. And they used the precursor to APL. It wasn't called APL at the time. It was Iverson's notation to spec out that whole system, how exactly it should behave. And then, just a short while after that, somebody got the idea that they could linearize this mathematical 2D small and big characters notation into something that looks like code and implement that on that same 360 machine. And Kurt Gödel would like to have a word, but they did. And shortly after that, my father joined IBM Research, and he was there for a few years, and then he established himself as an APL consultant. APL was never going to become a widespread language, because if you have less people necessary to write something APL, then the chief of the IT department would like to use something else. Then I started coming along to where I was born, and then I went to my first APL conference. Actually, I missed my presentation because I got drunk, whatever. And fast forward a little bit after that, I joined Dialog, which by then had replaced IBM as the leading vendor of, and especially innovator in the APL space. And when that picture was taken, I hadn't realized that when you wear wide-brimmed hats, you can't see your face on the recording. And during the very first conference, Dialog conference that I went to, and there was this expert APLer, Phil Last, made a presentation. He was working on a source code management system for APL called Acre. And occasionally, you don't just need programs, functions, you need constants as part of your source code too. It could be lookup tables, error tables, various settings. And funny enough, even though APL is the original array programming language, it actually did not, for all these years, have a notation for arrays, for constant arrays. You would always create arrays, which is really simple, manipulate arrays, even simpler, but you couldn't write, in general, any array that you wanted. So he had some ideas about using various brackets there, and he was giving this presentation I was attending, and it really got me started. And here we are, a decade later, and as you can see here, beta, the next version of Dialog APL will actually have such a notation, not exactly the way he designed it at the time or suggested it at the time, but definitely I think we've reached the right design for it. I'm not going to go through all the details of this, but you can, if you're watching a recording of this, then you can pause and look up things. But what even is APL? So let's have a look at that. APL was very ahead of its time in many ways. Things that are more normal today was definitely not the norm at the time. So various things maybe weren't completely unheard of, other than the array orientation. So when APL started, as you can see on the years, there would have been no computers with screens, and you'd use a typewriter. And a modified typewriter that could speak with a mainframe, a cloud computer, in modern terminology. And what was very unique at the time, though Lisp did exist, was that it was very much a conversational language. You would write messages to the computer, and then the computer would answer you back, which is kind of fun on a typewriter, and you can see the computer typing out things. And the convention was at the time that humans would write things indented a bit, and then the computer would answer in the left margin. So you'd write some code, and the computer would answer. I'll teach you a little bit of APL just to see what's going on here. APL is infamous for not using keywords. There aren't any reserved words in APL at all. Anything that's built in uses special symbols. And this is a Greek letter iota, which is a special symbol. And it's the index generator, because iota is like letter I, like index generator or integers. So an argument always, if you have a monadic, we call it, or a unary function, the argument always goes on the right of the symbol. So this is the index generator, or the indices of 6. So we get all the indices from 1 to 6. And just like we have this list notation or vector notation, which is literally just numbers next to each other, we can also use that for input. So to declare and fill and create an array of 2 elements that have the elements numbers 2 and 3, you would write 2 space 3. And if you try to tell the computer that, they will respond, yeah, sure, 2, 3. Then APL is array oriented in that things you know as a map or traversing over arrays and pairing up things is all automatic and implicit. So we can say 2, 3 plus 40, and the computer will answer 42, 43. No declarations, no loops, nothing. It just works like this. It always worked like this. So it's not exactly like a map, because notice here we have 2 arguments to the plus function, we call it. And if we give it 2 arrays, then it will traverse over both of them together. No counter necessary, and it just pairs up 2 with 40, 3 with 50 done. And this whole process is recursive, and including, at least today, the notation that you can just put things next to each other and it forms an array. So here on the right side of plus, we've got an array of 2 elements. The first element is itself an array, a list, 40, 50. The second element is a list, 60, 70. And when we apply plus, then we have also 2 elements on the left. So the first element 2 gets paired up with 40, 50. And we already know that that will give us 42, 52. And the second element 3 gets paired up with the 60, 70 for that result. So this whole thing is recursive forever. You don't need to loop anywhere or recurse or anything like that. Right, compound statements. So here is the letter rho. Greek letter rho, which is like the letter R, which is for the word reshape. And it is we call it a dyadic function or binary function. It takes two arguments. And whenever we take two arguments, one is on the left, one is on the right. And precedence-wise, it's very simple. Every function takes as its right argument everything to the right. So we could parenthesize the right argument to the reshape function, but there's no need to. And so this reads as 2, 3 reshapes the indices to 6. This gives us 2 rows, 3 columns, consisting of the indices from 1 to 6. You might also notice that there's no statement terminator, like semicolon in many languages. APL just finishes the line and then you're done. If you want multiple statements on a single line, then you can separate them with a diamond symbol. And that's because diamonds never break. If you tell the computer 2 statements at once, it'll just print the 2 results underneath each other. This is not a 2-element list of 2 matrices here. It is just 2 results printed after each other. However, if you parenthesize the expressions and you put them next to each other, just like any other things can be put next to each other, you get a 2-element list. Yes. Now you might begin to see part of the problem. So this example actually appeared in a long time ago in a text that was suggesting some further enhancements to APL, which added this more complete data system. And they sort of informally put parentheses around the 2 matrices to make it a little bit clearer to the human reader what's going on here. 2 matrices, 2 tables next to each other. But APL is a linearization of the original Iverson notation. And so we sort of want to read it linearly. If you read these 2 lines of code, then you sort of end up reading them like this instead, right? Because you go on to the end of the first line and then continue on the next line. If you want to read it like that, we'd have to have a very special 2D parser. It would be interesting. But of course, this is just a list of 7 elements, and the middle element is itself a table, which we could write in modern day APL like this. So this is 7 elements, 1, 2, 3, and then we have in parentheses 2, 3 reshape these numbers and continue. And that's not what we want. So what do we do about this? This is a real problem. People have already a long time ago recognized that for output, this doesn't really work day to day. They've come up with various systems that you can hook into the interpreter, some output processor, so it prints things a bit differently. A common format to use is this one. This is beautiful. You can see that it's 2 tables next to each other. And though it is made of individual characters, so it's really not a good form for input. Imagine having to type that. And especially edit that, that would be not fun. So what we really needed was a way to write, and it could also be used for output, of course, but write arrays. And we had a whole bunch of criteria that we worked out that this is what we wanted, and especially complicated by all normal brackets already having been consumed for various things and not even necessarily the same things across dialects of APL. So a lot of different vendors have slightly extended the language in various ways and used unused characters. And so I have to be very careful. But we started. The first step was that suggestion by Phil Last that I mentioned. And he said, okay, let's use the square brackets, which has before only been used for indexing and a little bit more, but only with like a single expression inside. And we'll put a diamond, which remember, that's what separates the statements, and therefore it can't appear inside a statement. But if it's inside brackets, then it's unambiguously something new. Put that inside, makes it clear that this is a new thing. It was invalid syntax before. And because diamonds are equivalent to new lines, that means that we could write our 2D array as a 2D text, but it was still parsed correctly. And they would look even very much like the normal output people are used to seeing. Good. For lists, didn't have any special notation because remember, we can just put elements next to each other, parenthesize if necessary, and that creates a list. So all good. We'll come back to that. For objects, which I haven't mentioned until now, but we can have these collections of name value pairs. He came up with this double square bracketed thing. And this is where the problems began. Because APL allows assignments, which is using the left arrow. But assignments are just expressions as well, and they have a pass-through value. So we can write things like this. So this is 6 multiplied by a, which is 7. If an expression can have an assignment like this, that means that we can have a table where every row of the table, should we say, is itself an assignment. Furthermore, we use square brackets for indexing. And APL is a bit unique in that you can, well, there are some other languages, I think Julia can do this too, that if you give an array as the indices, then the result becomes an array of the same shape as the indices with every element chosen according to that index, which means we can use a table for indexing. And that means we end up with ambiguous syntax here. What is this? Is this indexing the list with the table? Or is it a 2-element list where the first element is the variable called list and the second element is a newly created object? So no good. You could disambiguate with parentheses, but we really don't want to go there where you have to decide what something means without disambiguation. Okay, then you got rid of this double square brackets to avoid this problem in the object notation. But if you think about the object notation, it still has the problem here with the assignments. But let's say that you don't care, that we'll just default to one system. If you have an object which is a diamond-separated list of name-value pairs with the specification arrow, then if you have a single name-value pair, all good. What if you have no name-value pair? So supposedly this should be the empty object. However, APL allows multi-dimensional indexing as well with a semicolon-separated segment. So you do indices along one dimension, indices along another dimension. If you have a table, you need 2 dimensions. If you leave out the whole specification of indices along a dimension, it just means take everything along this dimension. So this is all rows, column 42 of this table. Which means for a list, a one-dimensional array, leaving out all the indices is just using open square bracket, close square bracket, and that would give you all the elements. You might think this is a bit useless. Firstly, it already works. We can't break existing things. Secondly, there are situations where you might want to do that. I won't go into the details of that. And we're back to needing to disambiguate, so that's no good either. The last came up with this notation for an empty object, and I thought that was ugly. Right, so internally a dialog. I was also working on the design of this, and I came up with using round parentheses instead. There was a problem though, that what about lists? Yes, we have a way to specify lists, there's just elements next to each other, but sometimes the elements are very big, say a text, a list of strings, and you may not want to have a super long line, there's no line continuation character in APL. So it would be nice to be able to write it over multiple lines, and then you really want a list notation as well. But if this is a list, then you would have to write a single column table as a sort of collection of lists, and things are getting really nasty to deal with. So you could make a convention that if you just have a single element, we treat it as a list, and this is then a column vector, a single column matrix. But then we're right back to not having a notation for lists. So finally, we said, okay, look, tables are sort of orthogonal things. Every row has to have the same length. They can't be ragged. They're sort of more symbolized by square brackets. Everything is angular like this. Whereas lists are more round, and it's similar to how you have to use parentheses currently for the list notation. And objects, which one should they use? Well, there's a practical consideration from before. Plus, objects are sort of like lists in that they just take a single index, but it's not a number, it's a name. So they're more similar to lists than they are to multiple dimensional tables. And with this, because of using square brackets only for tables and higher dimensional arrays, then we can write a single column like this. And because diamonds are equivalent to new lines, that means we can write a single column table as a single column, which is really nice. And the empty object can just be open paren, close paren, which is just a collapsing of no name value pairs. Notice we switched from from left arrow to colon to avoid the clash with the values coming out of an assignment. And it makes it very similar to things like JSON as well. There's a lot of more steps to this, but there's no time to go through all of it, and most of it is pretty boring. Then it came to actually specifying what it was we had come up with, and wrote a specification document, which you can go and read. And we went through some iterations as people were giving feedback on it, but most of it was good from the beginning after we hashed this over so many years. There was some human text, and there was some sort of more formal human text, but we had to introduce a lot of terms to explain this. And we also went with a more traditional formal syntax specification, though we actually ended up with a problem here because this is not a complete language. This was an extension to an existing language that it does not have a formal syntax specified like this. So when it came later for somebody to try to implement this, they got stuck on this, on the formal syntax specification, because what is even an expression? Which I couldn't really answer. That's that thing we use in APL. Also drew beautiful diagrams for those that like to read those. But I wrote an APL model to implement this. This is just the core of it. It's not the whole thing, don't worry. It was very, very simple and very stupid. And it just took some of this notation and transformed it step by step into a linear APL expression, and then finally evaluate that as just normal APL. You can see these presentations another time on these things. And then we had an intern. Camilla is a genius. She came in as into the company, and she wrote a C++ implementation and of this notation. It wasn't built into the language. It was as a function in the language that you could call on a string of this notation, and it would evaluate that, but return the proper value, APL value inside. And so she showed that it is possible to implement this. Those people that had their doubts because of all this overloading of symbols. So after she did this work, then our chief architect went and wrote it over in C, and this time integrated into the code base for the actual core interpreter, which is mainly C. And that made it possible to use it directly in line with the language, like any other part of the language. As for standardization, I addressed that in the documentation. I tried to do a lot of outreach. We held lots of meetings. We solicited feedback on things. We contacted the other vendors, our competition really, to try to get them along with this. And there's an APL wiki, and wrote not just specification, but also rationale for the decisions we made and the history, everything that's gone through. So it's all public information, how we got to where we ended up. And then finally, version 20, just about to come out. And this notation, which you can see these little matrices here. On the right, we have a function editor. We're editing a function, and in the code itself, we can have this two-dimensional notation for arrays. On the left, we have the interactive pane where we're using, again, even though we used to just write single lines of input to the computer, now write multi-line input and use it in line, and APL can also answer using the same notation. So that's where we are now. And learning lesson from this, I think it was good that we didn't have a standards committee, because the amount of iterations went through, and still it took us a decade to get here. It would have probably taken 100 years to get there if we'd had to have a committee meeting all the time. We had to have some forerunners that really hash things out between themselves, just a couple of individuals, and then go out and say, here, this is a proposal that seems really well thought through, and that's what we did. It was a problem for us, though, that there was no pre-existing standard. My colleague Carter will speak later today about APL standards and some of the problems with them. Interestingly enough, the APL standards do not really specify the syntax fully. And that made it interesting, shall we say, to deal with. And then, of course, I would have liked there to be a larger uptake of what we actually came up with. There was one hobbyist APL implementation that adopted this syntax. Almost. Syntax is the same. It gives a slightly different meaning to one part of it. And I find that's a bit sad. But as I said, dialog APL is definitely becoming the standard APL, and the other ones are sort of fading away. And then every once in a while, some hobbyist says, oh, APL is almost perfect. Let me just implement my own APL and make it just perfect. And then you have another hobbyist APL implementation that's slightly different. So that's really what I want to say. I hope that this little view into APL maybe gives a little bit of appetite to look into what APL even is. And go to our website, and there's lots of resources to get people started. We have been authoring resources to get people started with APL for over half a century. But even some modern things, you can even win money by just participating in this APL challenge. It's no requirements at all. You start, even if you know nothing, you can just go, and it will teach you everything you need to do to go through each of the 10 problems. And then for every problem you solve, you get a chance to win a little bit of money. APL Forge is also a chance to win money. That's once you get some more familiarity with APL. If you make something in APL, it doesn't matter, big, small, you can submit that, even if it's closed source. And you look at it, and if you like it, you might win money for that as well. So that's what I have time to say. We have a couple of minutes for questions, if anybody.
Hi, Adam. So I have a question for you. It's quite interesting that APL has had multiple different implementations, and at the moment, the one that I'm most familiar with is, of course, Dialog. And you mentioned that one of the challenges here is the lack of a standards document. That you described something in the BNF that was an expression, but this hasn't actually something that can be referenced from a standard document, which impacted the implementations. I'm wondering. Are there plans to bring about a more formal definition that can be shared?
We don't have any concrete plans to do it. There's an interesting question is who would do it? It sort of feels wrong that we as a commercial entity that's just one implementation would go and make a standard, and we would want to make the standard be identical to what we do. And getting cooperation with the other vendors is difficult. I tried that. There are some people in the process of setting up something called the APL Trust, which is supposed to be a more neutral organization, vendor-neutral organization, where people who have made a lot of money using APL put some money into that to kind of give back to the community, and they might be able to set up such a project to make a new specification. It will be a very interesting question what exactly to do, because there has been no standard for so long, and implementations have diverged so much that it's actually a significant work to port your code. It's not impossible. It's definitely easier than rewriting it in a different language, but it will be an interesting problem. We're definitely thinking about the idea of making a specification.
Right, and it's certainly very interesting that you mentioned that one of the benefits was that there was no standardization committee, and one of the drawbacks was the lack of this shared document where the design had been done together with multiple implementations. So it's an interesting tension that exists in the space of designing languages that are standardized, and standardization by its nature indicates multiple vendors. So APL is in this very unusual space in terms of standardized languages.
Yes, there's a core of the language that you can safely use. And you can port that back and forth, and it shouldn't make a difference which APL you use. But for the more advanced, the modern features, that's definitely a problem.
Well, following up on that, wouldn't it make sense to at least like standardize or specify that common core that they have?
There are actually two ISO standards for APL. And the extended standard, the newest one from 2001, it does cover mostly the core. But stick around and hear what my colleague says. There are good reasons why the various vendors have not followed that spec. Okay. So the spec has issues in itself, and there are aspects of the language that make it difficult. So mostly you could do that, and we could maybe make some kind of appendix to that or a new version of that and saying, okay, practically speaking, if you use these parts, you're safe, and then everything else is implementation dependent.
I also had one very primitive technical question. So in the syntax you ended up with, like, seems there's still overloading of empty parents as both an empty object or an empty list, or does one of these not exist?
Right. There's no problem there. APL is weakly typed, but all arrays have a type. And therefore, you cannot write a literal array without specifying its type. So an empty, if there was a notation for an empty list like this, then it would have to have the type included. Because the open paren, close paren has nothing in it to show what the type is, that cannot be a notation for an empty list, and therefore it's only for an object. And this array notation does not allow you to write arbitrary empty arrays. Some empty arrays you could write, but the way you would do it is it's very simple in APL, using APL primitives to take an array and empty it out. So the recommended method, and when we generate notation, this is what we do, is we just need to prepend 2 characters in front of a bracket or a parenthesis to empty out whatever comes after that. And that allows you to specify what the internal type is, and then you empty it out immediately. It remembers its type.